So we're going to start off with a practice problem. I am going to pause this video while you guys work on it, so please help me remember to unpause it while I'm talking about it. And here is the situation we're going to be looking at. Now, keep in mind that when I talk about bridge problems, ultimately they are equilibrium problems. So I'm going to call this a bridge problem despite the fact that here is the situation. The situation is some human is sad. Okay, if you want me, cool, me. And I lean up against the wall like this.
Yes.
Draw the extended force diagram on Spainhour for the sake of people online.
I need the bridge.
I am the bridge, or any human in this particular case as well. So here's your human.
Is it the force is on you or on the wall?
I am your bridge in this particular case, so it is me. Now, one assumption that are regularly made on this type of bridge is the following. We are going to assume there is no friction in the wall. Okay, that is both true and untrue. Okay, the type of friction that it would be in the wall is static friction. So as long as there is like no tendency up or down, there would not be friction in the wall, because it would pull the opposite of the way that you want to go. So that being said, I said no friction in the wall, but do keep that in mind. Also, as you're drawing this, you can check yourself to see if you're right, because remember that all torques should be able to counter each other, as well as, and this is absolutely going to be your friend on this one, forces up better equal forces down, forces left better equal forces right. So if you're done and you've only got something left, well then something is in trouble on that particular front. Okay, give you a small amount of time. People online, see if you can't try to also do the extended force diagram. Oh, also, maybe this messes you up. I'm going to go ahead and draw the legs probably a little bit less accurately here, so it's just all in like one location, so you're not trying to overcomplicate that way either. All right, pause in the video. Here we go again. All right, so let's see what you got. What forces you got?
Gravity down.
Gravity down from where?
Center.
Center of mass. Let's go ahead and use another color so it's obvious. Okay, here's force of gravity, center of mass. Cool. What you got next?
Force of wall.
Force of wall, which, by the way, just a heads up, if you had called it force normal is fine. You just try to be very careful, obviously, about using a couple force normals. So force wall probably makes the most sense in this particular case. That being said, given what I said a moment ago, force normal is probably where? On the feet, pressing up right here. Also, I don't love this about my picture. I think that's going to make it a little bit wonky later. Let's do this real quick. So it's just more of like a rod situation of a person. Here we are.
It's a very same person.
It is, certainly. Okay, force normal here. Okay. Next, what you'll notice out of this picture is you have a force up, you have a force down, you have a force right, and what do you seem to be missing? Force left. What force is it in reality that causes friction? And where's friction going to be applied at? At the feet. Just a reminder, because this will help certainly later about this. Remember, force normal and force friction are directly related because force normal is electrons pushing on electrons, and force surface friction is the positives pulling on those electrons at the exact same time. So it makes sense that both of them should be at the exact same location. All right, I'm going to give you a small piece, relatively small amount of information from here, and I'm going to give you some extra time then to try to see what you can't do about solving it, and then we'll be along a little bit later. Here is the situation. The human in question weighs 180 pounds. The human in question is, let's go ahead and use another color here. We're going to say 1.7 meters tall. 5'6". And finally, technically it's 1.67, but I rounded for simplicity of math. Okay, and finally, the last thing I need to tell you is this. We're going to say that the angle between that person and the ground down here is 70 degrees. With that information, you should be able to find all other forces in this problem. I'm going to give you probably about 5 to 8 minutes to attempt to do that, and then I'll be along afterwards to kind of make sure that you got it the right way. Anytime you are done, let me know. I can check your work, or I can tell you what the correct answer is. Off you go. Pausing you guys to start doing this. Okay, we're looking at firstly, lever armed again to the center of the person was how much? Apologies for repeating this for people online. I screwed up again. Okay. What's the lever arm from for force of gravity?
0.85.
0.85, half of that, and of course force of wall is 1.7. Okay, we already calculated right over here. Okay, that's, nope, screwed up. 1 pound is 4.45 newtons, so force of gravity is 801 newtons. Okay, now the messy piece usually is angle. These, don't worry about the angle. Why are we not worrying about the angle of the bottom two? Because they put out how much torque? Zero. Why do they put out zero torque? Correct. Put the fulcrum of the leg specifically so that their torques would cancel. Now, watch here in the picture. I go from lever arm to force. Everyone see how to draw that angle? Drawing, it's the first piece. Then you got to go, well, Spainhour, you told me 70. Can't I just plug in sine of 70? No, because that's not always the angle that you need. But what you will always find is that you can always find a right triangle to be able to get what you need. If that's 70 degrees, and that's a right triangle, that makes that 90 degrees. That makes this angle up there the complementary. So what angle is this? 20. Correct. So the angle for your torque with gravity should be 20, just the complementary of the 70. Yes? Because 70 plus 90 plus this guy has to equal 180 in every triangle, right? And since it's a right triangle, what you could really just say is these two angles have to add to 90. All right, next though, watch here carefully. Okay, here, this is a little bit tricky because of how I drew this person, so I apologize. Watch this. What about force of wall? Force of wall has to be this angle. What angle is that one going to be? That one's going to be 70. And if you don't see that, here, let's draw this out a little bit bigger. Okay, well, that's going to do it. If this right here is 70, then this also has to be 70 because it is, again, alternate interior. If you don't like the rule of alternate interior, fine, watch this. Did we just figure out what this angle was a second ago from the vertical to the lever arm? It's 20. So if that's 20, 20 plus what gets you back to 90 degrees? That has to be 70 right up there. Now, let's finish off our work right over here. Sum of torques has to equal 0, right? Cool with that? Neither of those two on the bottom cause torque. This one is positive or negative. Gravity is going to cause positive or negative torque.
That's going to cause
Positive torque, correct? And the wall is going to cause negative torque, which of course you sort of knew had to be the case because as we mentioned before, you have to have both a positive and negative to get to 0. So that means the torque of gravity has to equal the torque of the wall. Everyone cool with that? Now, the equation is lever arm of gravity times force of gravity times sine theta of gravity. One thing you're going to start, we haven't dealt with this very much in problems. So what did I do? Oh, thank you. Okay. One thing you want to be weary of is whenever you put sine theta, make sure you put a subscript on that thing as well to remind you that not all angles have to be the same either. You're not just throwing 70 wherever it is you want. And this would equal lever arm of wall, force of wall times sine theta of wall. Of course, algebra here is pretty easy. What do I need to do algebraically to get force of wall? Lever arm of wall times sine theta of wall, and of course that would cancel these guys out over here. And now let's go ahead and plug our numbers in. What is the lever arm of gravity again? Remind me? 0.85. Okay, meters. What is the force of gravity? What should, I don't know. Try that again. 801 newtons. All right, times the sine of what angle should we be using here? 20 degrees. Divided by, what is the lever arm for the wall? That should be 1.7, right? And what should the angle be for the wall? Sine of 70 degrees. Throwing that all into your calculator, what do you end up with? 140, like 7 or 8. Hey, check to make sure you're not in radians. What's up? 120? No, it should be 140. Let's check it real quick. Throw a calculator myself.
I got 145. I got 145.77.
Yeah, I mean, there you go. 1.85 times 801 times sine of 20 divided by the open quantity 1.7 sine of 70 closed quantity. 145, yeah, 145.77, so we'll go 146.
Or 150.
I suppose if you wanted to be a jerk, I mean, who would do that? All right.
I don't know who would. It's not like his name.
She said, or 150, and I said, who would do that? All right, now, I said I wanted every force, and I do want every force, except that is absolutely the hardest part of this, because how do we calculate the other two forces we don't know?
We just know that.
Right, you do need to show the work. You do need to show the
We
work.
just have to show you something of force.
Correct. Here it is real quick. It shouldn't take you very long, but here it is real fast. It would be sum the forces in the x equals mass times, well, actually, let's even go even one step because it's equilibrium problems. I'll let you go to 0. And what are the sum of forces in the x based on that picture?
Some forces in the what they said.
Force friction minus force wall equals 0, and therefore force friction equals force wall, which of course we already calculated to be 146. And then of course beyond that we have summing the forces in the y equals 0, and that would be positive force normal minus force gravity equals 0. So force normal equals force gravity, which you already calculated is 801. Now, what? What's up?
Why is the wall negative and the friction positive?
Because he wrote it wrong.
Oh, you're right. 100%. 100%. To counter that, you are right. I did write it wrong. I did it the opposite way last hour, okay? And I realized that that makes something a little bit messy in a second, okay? But just as a heads up, if you draw the person, which I literally did this problem last hour, I set up on that wall. So here was the situation. And that's why I switched it, is honestly all it is. Okay, all that you need to get out of that is that of course, it's going to end up with the same math either way in that particular front. Okay, so the back half of this question is the following, okay, which is not meant to be too hard. It will appear hard at first, though, just as a warning. Okay, let's say that wall disappeared, or it was a temporary wall and someone took it away. How much is that person currently going to angularly accelerate? Helps? This is the problem or the equation that we ended with yesterday. Okay? The inertia graph, correct. Keeping in mind that our force normal and force friction probably still going to be there. They would, except where am I probably going to be rotating around as I attempt to fall flat on my face? Yeah. Also, if you don't like the whole wall disappearing thing, here is that question more seriously. A person leans over at an angle of 70 degrees to the ground. You expect me to fall flat on my face right now, right? So if they do that, how much are they about to angularly accelerate their entire body in that particular instance? So basically, use the exact same extended force diagram, just do what different? Don't put force of wall, correct. Don't put force of wall. And also on this problem, instead of setting sum of torques equal to 0, you're going to set sum of torques equal to correct. What are we going to set? I like the idea on your page right now. On your page right now, just sum of tau equals to not 0. Yes, I alpha. Moment of inertia times angular acceleration.
Oh, I have them.
Okay. A reminder from yesterday. What is your equation for moment of inertia?
Torque equals that.
No, individually moment of inertia.
Oh, mass times radius.
Almost.
Mass times r squared.
Almost. That's not what I'm looking for. That's not the different issue I have. The issue I have is this. Remember, you use mr squared if what is the case?
If your hoop around is
If all the mass is at the exact same radius. Or another way to say that is if it is an orbit around a particular object. Okay? Or as I'm rotating, where am I rotating around?
You're rotating about diameter.
No.
This
Around my feet is correct. So, is all of my mass at this radius?
no.
Sadly, no. Now, the solution is very simple. All it's going to be is you go to this chart. There will be no shapes outside of this chart other than if the thing is rotating at some distance. Which of the following shapes probably is best suited for what we are looking at here? Rod about the end, correct. So off you go. See if you can calculate angular acceleration now.
Well, I don't know.
Oh, but you
I do,
totally do.
Stop, because you do that divided by that. And then you have...
So all we're doing here is essentially taking the wall away from the problem. Like I said, if you don't want to imagine the wall disappearing, this is just a person falling flat on their face. Person is going to be rooted by the fact that friction's kind of holding their feet in place, and so this is where we put the fulcrum. Remember my rule of the fulcrum the other day was this: you can place it wherever you want as long as that spot's not accelerating. So when it comes to bridges, that means literally put it anywhere. But when it comes to a person falling flat on their face, you have to, or you should know, to put it at their feet. By the way, this reminds me of something that I forgot to mention on the homework problems. You know how you can put your fulcrum anywhere?
Yeah.
Okay? There is a word phrase on the homework that some of you have probably figured out, but it said calculate the torque, and then it'll say about this particular spot. You've seen this phrase, yes or no? What that is doing, by the way, is that saying like, hey everybody, everyone put your fulcrum here, and if you all put your fulcrum here, then we'll all calculate the same torque. Because fulcrum can go anywhere, if I say calculate the torque about the feet, that simply means put the fulcrum at the feet. All right, so in this particular case, again, we have sum of, let's actually use yellow real quick here. Sum of torques equals I alpha. What about this picture tells you that this equation has to be the case? What about this situation tells you that you have to do this? That's what I was looking for a second ago. But yeah, if you want to go here, I don't like apples. Trying to make a reference to a popular movie. It's popular in my age, not yours. All right, moving on. It was a Good Will Hunting reference. Do you like apples? Okay, moving on. So in this particular case, number one, yes, if you look at Spainhour, he's going to be angularly accelerating. When this person follows over, it's going to be angularly accelerating, tells you to use that equation. Or if you do an extended force diagram, you can see that I've got torques that absolutely cannot be balanced, which means absolutely this is once again going to be the case over here. How many torques are there going to be in this situation, though? Based on where we put our fulcrum, how many torques are there going to be? Just one, absolutely. So the sum of torques is just what? Torque of gravity, correct. From here, you are welcome to do this one of two ways. It's obviously a bunch of you guys punched it into your calculator, that's fine, but you also want to get used to showing the work. Okay, you can either go ahead and somewhere to the side calculate the torques individually and the I individually. Me personally, as you get good at these, it's vastly more efficient to just write all of it out at once, and that would look like this. This is lever arm of gravity times force of gravity times sine theta of gravity. Of course, that sine theta is because, once again, it is not at 90 degrees. Okay, and that would be divided by the I, which we mentioned a second ago, has to be this rod about the end because not all of the mass is rotating at the same radius. So this is going to be 1/3 ml squared is equal to alpha. Plug your numbers in here. You get, once again, this is 0.85, just like it was before, times 801, just like it was before, times sine of 20. Now, I mentioned this at the heart. We'll mention it again. Okay, the phrasing I used when calculating this angular acceleration, as I said, calculate the angular acceleration right now. And the reason why is because as this person falls, what's going to happen to that angle? It's going to get larger. It's going to get closer and closer to 90. So technically what happens to torque and therefore angular acceleration as a person falls? It gets bigger and bigger as a person falls in that particular thing. So all that means is we can only calculate it at a particular moment. Then this would be 1/3. We already mentioned this earlier, but I don't know if I mentioned it online. To get mass, you know that force of gravity is 801. So you just divide by G. And that gives us our 81.7 kilograms. So that's 81.7 kilograms. And as we did the other day, we need length, not radius. So this would make this 1.7 meters, and that whole thing is squared. So the angular acceleration should be 2.96, and what are the units on that?
Radians per second.
Okay. Last conversation and we're done. If I wanted to take that angular acceleration and I wanted to find out what the linear acceleration is of the top of my head, what would I need to do?
Kind of matter.
Nope. Easier than that. What's that?
Find radius.
We're almost. We know the radius. What's the equation that you would need to use?
Acceleration tangent.
And in this particular situation, what would radius slash r be? Because I specifically asked what's the linear acceleration of the top of my head.
Distance from your
Be
head.
the distance. Yeah, it's like you basically what you do is you treat the top of my head as though it's going in a circle, meaning this would just be 2.96 radians per second squared times 1.7 meters. What do you get? 4 and change, if I'm not mistaken.
5.
Is it 5?
Yeah.
Like almost exactly.
5.032.
Okay, 5.0. Yeah, we'll go with 5.03. Okay, here's what I want to point out about this number and what is the best check in a problem like this for if you're going correct. Number one, here's why this number perfectly makes sense. It's less than 9.8. Why does it absolutely need to be less than 9.8?
Because you can accelerate quicker than gravity.
Right, gravity is what causing me to fall over. You would not expect the top of my head to accelerate faster than 9.8. Next question, look at the extended force diagram. I promise I'm almost done. Look at the extended force diagram over here of the person falling over and answer me this. Why is it not 9.8? Why is it not 9.8 exactly?
Because there's
Specifically, what force?
Normal.
Force normal is what's counterbalancing it. Now you might say, unlike the last problem, in the last problem we said gravity and normal are equal. And if they were equal, then how much should I be accelerating? Should no, 0. I wouldn't be accelerating at all. So actually what ends up happening here, we don't need to get into the weeds, but you can use kind of just reverse logic on this. What does that mean happened to force normal as I started to fall over? It decreased, which kind of makes sense. If you watch a slow-mo video, my feet probably are still touching the ground. Are my feet probably being pushed up by the ground the exact same way? No. As a matter of fact, as I get further and further over, they're pushed less and less and less. And actually, as they push less and less and less, guess what the top of my head heads towards in acceleration as that angle flattens out? Heads towards, what is the top of my head acceleration to head towards as I flatten out?
Center of gravity.
You know what, I'm looking for a number. What number? Well, the top of my head,
9.8.
9.8 is what that's going to head towards, and that makes sense because as this angle heads towards 90, you would expect obviously more torque and therefore more angular acceleration and therefore blah, blah, blah. You get that? Actually, I'm curious on this. I'm going to check it real quick before having you check it. If I assume 0.85 times 801,
That's the right number of
okay, divided by quantity.
Right.
No, that doesn't quite end up the same way. Never mind.
Wait.
All right, that's it for this problem today. We're just going to practice with homework the rest of the time.
Wait.